task. Yeah,
This step must be sequential.
the which one should be sequential?
Like I'm checking that to be two first processes.
Right. Yeah.
Yes, like you upload the data set, then you go for when instruction, function, motion, production.
Right.
So I'm saying for this step,
Right.
this task,
Right.
it must be sequential.
Uh,
Okay, interchange as the way I want.
right. So I will. Okay. That's a very good question. I think what he's asking is, does the step have to be sequential, and could we rearrange the order? Is that the question you have? Some of them you can rearrange the order, some of them you cannot, right? If you did spatial smoothing first and then did motion correction, it would be messy, right? But and therefore perhaps you should first do the motion correction and then do spatial smoothing. Can anyone tell why we should do motion correction first and then spatial smoothing? Right, right. So you would make the images which are not registered, you are making them smoother. So trying to register is going to become more difficult. All right. Any other question? Okay. Um, okay. Uh, Joshua, you had a question? Okay. Um, so for the task activation, there was a set of steps that we followed, right? Very similar to, almost identical to this one, right? And as I had said yesterday, for resting state, we also analyze the data very similar to the way we analyze the task activation data, right? So in this data set, which is from the Midnight Scan Club, what we are going to do is use the resting state data and then do the pre-processing. And then what we will do is we will take a voxel from the sensory motor cortex. Okay, the sensory motor cortex is what we had generated yesterday, right? The left and the right motor cortex. So we will take um, a voxel time series from the sensory motor cortex, and then step is always like to load the data. Then we have to load this NILearn, NIBabel, NumPy, and Matplotlib, right? Um, then we use oh, FSL, right? So okay, so this one is still running. So it will install FSL in the local directory. This takes about 11 minutes. And once it is done, um, we can then basically run the commands through FSL, right? Once we finish running through FSL, I will also try to show it to you using a different package called AFNI, where we can also analyze the data. Um, is everyone able to use the Digital India? It's working. The link is working. Okay, because it showed a runtime execution error. Okay, let's just wait for a few minutes. Okay, okay. So I'm basically configuring the FSL, and then the first thing to check is the motion correction. Right? So again, this is just loading the files basically. And this is the next step is brain extraction, right? These are the commands. Um, I haven't gone through um, detail with this command, but this gives you many different options, right? If you use -O, it will generate a binary mask, right? If you want the image to look like the anatomy and preserve the anatomy, then you don't use -O, right? If you want to keep the skull as a different image, you can just use -S, right? That will generate. And then this is to do the BET. Again, this is showing the data and the data size. If you're interested, you can just click, it will tell you the size of the data, right? So this is the T1 weighted image, the anatomy, right? Um, and this is going to plot the anatomical like before for the task data, and it will plot the three orthogonal slices. Okay. And then we make it go through the BET data. So now we can see uh, the data without the skull, right? Um, Again, I should emphasize that this is not a simple thresholding where we can find the anatomy from the skull, right? There are other methods which is used to find the volume and then exclude everything outside the brain volume, right? It would not be possible to find the threshold. If anyone can show me, I will be, very pleasantly surprised as to how you're setting the threshold. And it is difficult for the same thing I showed you yesterday, right? When you set the Z score, whether 2 or 3 or 4, right? So you have false positive and true detection. If you use simply intensity-based thresholding, there will be some voxels which is inside the brain which have intensity like ventricles and so on. Intensity is less than of the skull, right? So that is why other features are also used. Okay. The next thing that is done is to display um, the BET anatomical on the original anatomical. So you can see the image and then a colored map will be displayed to show, you know, how it is done, right? And again, as I have said, like when you have time, you should go through this because this shows different ways in which you can do the thresholding, right? Then is McFlirt, and again, this gives the option, and this has the cost function, like what criteria to use, whether to use mutual information or normalized correlation or least square or Wood's approach is when you have two images, the ratio should be minimal, right? So that is that approach. Right? So this one will take a little time because this one has 818 data set, right? So for a long time period, it is there. So it will take, so again, as I had mentioned yesterday, the way it, Rahul, you had a question?
The data points will be listed.
Yeah. No. The task was 104 data points. The resting has 818 data points, right? And so it is doing the registration now. So before it would take first as the reference, compare the second to the first and adjust the second one to match it with the first. Then it would do the third with the first, fourth with the first, right? Um, there are, of course, ways in which if you think if the subject moved at the beginning and you want to register with the last image, you can set the last as the default. If you want to register with the mean image, you can also set the mean as the default, right? So there are many different ways. If you want the anatomy as a reference, maybe not in this package, but there are other packages which would allow you to do that also. Okay. Huh? Oh, which one is the best one? Okay, the best one depends on the question you are asking. A lot of times, typically, um, least square is good and it's fast. But sometime if you are trying to, um, let's say, give anesthesia, right? With anesthesia, there is a change in intensity. So in that case, least square won't work well. So in that case, you should use mutual information, okay, or other criteria, but generally mutual information is good, okay, right? So it is going through the different number of data points, right? So it will go all the way till 818. Those of you came a little late, like go through chapter like day 3, which is resting state, because by the end of this class, I want everyone to have generated the resting state images. So now many of these packages, after you use different options, it will write out even a paragraph for you to be used for your paper, right, with references. Okay, so the motion correction is complete. Now, again, everything we are doing is identical to what we had done for task, right? Um, and here you can see some variation. Obviously, the variation, if there is any, will be along the edges of the brain or large vessels. And then, like yesterday, we will look at the motion parameters, right? Remember when I displayed the plot function yesterday, the signal went up, right? So this is how it looks like. And so one way is to plot x, y, z and translation, and then x, y, y, z, and x, z rotation, right? The 6 parameters. These are the ones. Yesterday we also computed another motion parameter. Does anyone remember? Very good. Frame-wise displacement, FD. Okay. Right. So this person, so the last one, right? Um, the the range. Does anyone remember? Does anyone remember the range? We were saying, oh, it's between minus 0.05. No, it was minus 0.05 to plus 0.15, right? Yeah, and so we were saying the subject is a good subject. In this case, though, um, this is 1.5, so this person did have some motion, right? Um, so after that, we will be, um, right, this is the frame-wise displacement. And in this case, there are, if we set at 0.5, there are several instances where the person has moved, okay? Yeah. So after that, what we do is, um, it will of course correct, right? But if it's more than a few, let's say 2 millimeter, then I would check the data before and after, right? Okay, and this is, right? So again, this is doing for, like, the flirt is for transforming the anatomical data to the MNI template, right? Again, these are the things like one has to based on, but you can typically use this as a default, right? If you're doing healthy subject, you can use this as a default. Only for specific cases you would have to change, right? And this is functional rest. This is the anatomy. Then this is the MNI template. And again, the MNI template is useful for most of the cases, only in specific cases where you think the anatomy of the subject has been like is not won't match, only then MNI should not be used, right? So, and the example would be if you are using infants, perhaps you cannot use, or if you are using someone like a bunch of subjects with brain tumor, then perhaps MNI is not the best way. And then we align the anatomical to the MNI template. And then display this. And then check. And again, as I want to emphasize that now, like all these things can be written as a script and you can run across all the subject. But I would highly recommend, even if you're doing 1,000 subjects, like, spend at least like 10 seconds, on each subject to see how the registration is, right? If you are not careful and there are a few subjects where the registration is not correct, then all your analysis is going to be suboptimal, right? You may get unwanted results. So, right, so this is where what Pratik has done is that he is not processing the data, because to run the data, it took him 30 minutes. So he has, like, using these steps, put the process data there, and we are just running that data. But I would suggest that you should try just running, like, copy the data somewhere else that Pratik has, and then run the data and see what, like, how the result looks like, right? So then we do the transformation between the MNI and the anatomical, right? And so then we are going to do functional, right? Functional image on the MNI, and this is the registration. Again, it looks quite good, right? Right. So far, everything we have done with resting state is what we had done with task, right? So now the analysis for resting state becomes different from task, right? And the analysis for resting state, in my opinion, becomes easier, right? So what we do is now in this case, we will go and find out, right, a seed region in the brain, because it is in the MNI template. From the coordinates, XYZ coordinate, we know which region is associated with which coordinates are associated with what regions, right? And what we then do is we find out or identify a bunch of functional regions, right? In this case, um, we are identifying only like specific region because we know we are interested in the sensory motor cortex, right? And so we find the sensory motor cortex at this location, right? Minus 38, minus 22, 60 with a radius 6 millimeter, right? So then what we do is we use this command to generate a sphere of radius 6, right? So it would be like um, the spatial resolution of this one is, let's say, is it 3 or 4? No, no, what is the spatial resolution of this data set? 4, right? So it is 1.5 voxels surrounding this, right? And we take that as our seed region, right? And then what we do is we extract the time series for that region, right? So first is on the MNI template from XYZ, we know which region is what, and then for this one, like the coordinate was like minus 38, minus 22, 60, right? So that's the location. Now I want to display the time, right? So now I simply go to my functional resting state data and then generate the time series, right? Uh, right, right. So because it knows what the spatial resolution is, right? That's what I'm saying, that that is the default I have used. But you are welcome to try 8, right? I would say you should try 8 and see what happens, right? So we have the time series, then we generate the connectivity map, right? So with the time series, what we do is we take the average time series, which will have how many data points? 818, right? Because that is the time series. And then we are taking that time series and starting with 000 001 all the way to 64, 64 by 36, right? So we will do for the whole volume, okay? And then do it. So the correlation is done, right? And then seed-based correlation map is created, right? And now we run to see how it would look like, right? So like this is the moment of truth, right? So this data, I have no idea, I didn't collect it. And only thing we have done is taken a time series from the motor cortex and then correlated with every voxel in the brain, right? And I would say that if nothing else, we should be very careful how we process our data, and any observation that we see should be reproducible, right? Um, right. So while people can have many different hypotheses as to why we see connectivity during rest, this is the data, right? And this is the result. Now it is up to us how we interpret the results, but the most important thing is the finding, right? Anything that we do should be reproducible, right? Any question, anyone? Isn't this amazing? All right, so based on um, actually till 2 weeks ago, I had analyzed this data, but not, I had never looked at the task and then rest. So I thought it would be good to see, you know, how the task looked and how the rest looked, right? And so this is how the rest looks like. And then we can do a comparison between rest and task, right? Right? So while actually, yeah, so while this one is rest, this one is task, right? Again, I think um, you can play with the threshold, right? It's always a question as to what threshold should we use for resting state, what threshold should we use for task. But the fact that they are so similar um, is like good, right? Um, okay, so there are several things that I had done in the original paper that I haven't done here, right? And in the original paper, what I had done was I had used uh, like temporal filtering to look at the data and remove some of the noise, right? Also, as I had mentioned, I could only collect 512 data points, right? So um, I was limited in that way, right? I could like, it's not me, the machine would not allow me to collect more than 512 data points in a single slice. So from that, I had to get as much signal as I could. Also, because there was criticism that maybe this is respiration, maybe this is cardiac, maybe it's some kind of artifact. That is why also I was using filtering to look at the frequency spectrum and then remove these effects, right? So has everyone been able to replicate this result? Those of you who haven't, maybe please try to do that. Okay. So once you have it, then we can try other locations, right? In this case, we used, um, you know, let's say minus 33, right? Minus 38 minus 22, 60, right? What would happen? It's XYZ, right? So what would happen if you took plus 38 minus 22, 60, right? It would be the, and then used it as a seed and then do the same analysis. What would you get, right? So try that. And if you do that, you can keep the other like values the same and then look through that. Here you can also change. See here the threshold is 0.25. We can also play with the threshold. right? Like all these have the same type 1, type 2 error problem, right? So if you set a lower threshold, um, you will get more activation, but many of them would be false positive. But at the same time, if you used a higher threshold, then you may not get much, right? So with zero point 0.4, you see something, but it is not as robust. Okay, right? So Joshua, you have results? Yeah. How about others? Point 0.3, 0.2. Okay, all right. Okay, yours is also 0.25. Okay, yeah, play with the threshold, or else change the coordinate also and see what happens. Oh, and you can see that. Very good. Okay, good. Yeah, yeah. Huh? That is generally on the, that's like ventricles. I think it is okay because so so between the skull and the brain there is CSF, right? And so that is what it is. So if we cannot easily see the contrast, but that is what it is. Okay, good. Change the threshold. Hmm? Now, why didn't you start before? Okay, it will take 10 minutes. Yeah.
Not regarding this, but suppose when I'm doing it on the interface,
Okay.
From the OrthoView Atlas, I open the meetup region
Right.
and I compare. So
Right.
that percentage that it shows, this is
Right.
a probabilistic
Yeah.
activation.
Right.
Where is it acceptable? Like,
Oh, no one knows the answer to that. Eh, Okay, I mean, there are ways to do, but there is no easy answer because you're physics major, right? Have you heard of receiver operating characteristics, like false positives? And so if we really want, we have to use ROC curve to best determine. Yeah, yeah. Okay. A reference is from the mask, right? So there is a ROI from which we can find the mask, but there are other ways to find the reference also. Okay. I'll show you later. All right. Maybe Joshua, can you come here? So Joshua has been able to do it for the other coordinate also. So he's going to show you how to do it. Come. Okay. You just use you used 8. Okay. It's not running. Is it? Oh, wait. If any Shreyans, you are able to do it. Okay. Okay. Right. 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 Okay. Um. Okay. Thank you. So basically, by changing the coordinate, as long as you know where you are, you should be able to generate multiple functional network, right? Now, in this one, if you can find out where the visual network is, of visual, the coordinate of the visual cortex, you could also set that as a seed and then rerun the analysis, right? And it would, I'm pretty sure, activate the visual cortex. Okay. Yeah. Right, right. Okay, that's a very good. Speak louder. Yes. Right, right, right. Can anyone answer that question? Yeah, but so you could use MNI and Atlas, but in this case, we had the finger tapping data also, right? And that is what we had used as the reference, right? You can find um, the coordinates from of the finger tapping or left foot or right foot, and then use it as a seed region, and then perform the correlation. You should get the sensory motor cortex. All right. Yeah.
What is comparing task versus rest? What impressed you?
Right. So in some way, this is not comparing task versus rest. This is just validating our results that, okay, even during rest, there is this information which is in the resting state data, which is unique to the sensory motor cortex, right? And you don't have to do the task to identify the sensory motor cortex. Yeah. Any any other question? Yeah.
So what we are saying is that even without doing any task, we are getting the results that we are
Right. Yeah. That is why my paper got rejected 4 times because like people did not like like I think, okay, there's no professors here, right? So my papers was reviewed by mostly cognitive scientists and psychologists and neuroscientists, right? For them, everything is based on task, right? And therefore, some student telling them that, hey, without doing any task, I can get what you are getting is not good. So, okay, so play with the coordinates, like try to change a little bit here and there, and then see how much variation you get, right? Um, like play with the coordinates, move it by 1 voxel, right? And then see, are you seeing the same, right? So try that and get an, I really want you to get an intuitive feeling about this connectivity, right? And try that. And later, what we are going to do is, again, this is on the raw data. I haven't done any filtering, nothing. When we do filtering, the result, you know, becomes even better, right? So now try for the next like half an hour by changing the coordinates. And it would be good to like save the screen, like what coordinate you used and how the image looks like. Try for many different coordinates. If you can, also try to use the visual cortex if you can. Okay. I can. So there is a website called Neurosynth. We have a medical, there is someone with a medical background, right? Okay, just help me identify if mm, where would the coordinates for visual cortex. Yeah, like if I had to locate the visual cortex, where would it be? No, just see on the location. Is that the visual cortex? Okay, so then the coordinate is 18 minus 84 and 8. Those of you have done, maybe try this coordinate and see what do you get. Is this an MNI? Right, Yeah, so try that location, try this location and see what do you get. Have you, what happened? Yeah. Seed coordinates and right, 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 right. So right, so that gives some information about how far down the area you are willing to take the correlation into account. But now we can like ignore that part and just focus on finding the seed voxels. So what I'm going to also do is um, use a different um, like show you the same result using a different um, pipe like package. Yeah. Oh, I'm just using AFNI, so just give me 1 second. Right, so this is another package. What was it? Minus 38? Yeah, 60. You can randomly try different regions. So, all right, so this is again doing connectivity analysis using a different package, right? Where I can display the time series, okay, which is here. And then what I can do is I can go to any location I want. Let's say I think, right? So this is my visual cortex, right? Do you see like how when I'm focusing here, most of the connections are in this region, right? If I went to some other region, if I was to do analysis like what you are doing, I could just go here and then analyze, and then I can show that they are indeed connected, right? Of course, within connectivity is always going to be like left to left is going to be greater than left to right, and right to right is typically going to be greater than left to right. Okay, so these are like different ways in which we can also measure connectivity. Okay, but I think the FSL one is okay. Can anyone tell me what would happen if I went to the edge of the brain and did connectivity analysis? The edge, like let's say here. So I haven't done anything. This is the raw data, right? I haven't even removed skull strip. I haven't done anything. Like I haven't used BET or MNI template, nothing. This is the raw data. So if I go, let's say here, so if I go to the edge, generally I would see most of the voxels around the edge, right? Maybe my threshold is a little high, so we don't see anything, but that is how the edge would look like, right? It would be mostly on the edge. Now, if I do ventricles, right, because it's mostly CSF pulsation, it will, remember like when we had done the mean and the noise characteristics, the signal was high here because it is CSF pulsation, right? So by clicking, like by doing these analysis, I can focus on any region and then and see how does the rest of the region connected, right? Um, so these are like two different ways in which we can measure like connectivity using two different packages, right? One is using FSL. This one is using AFNI. Um, like installing AFNI is a little difficult because you need a Linux workstation, and um, that is why I didn't use it for this course, but we can use this in Linux using AFNI, right? Right, right. So, right, so DPABI is also another package to do resting state analysis. It's written in MATLAB. So it's also a very good package. You can use it if you want. Uh, um, so I typically use AFNI more because like the person who wrote this, Bob Cox, was one of my professors when I was doing PhD. And then when he retired, my student has now taken that position, right? So like Paul Taylor, he's very, very good. So he's developing AFNI. So therefore I use AFNI more often. Right? So again, there are many different ways to analyze, but regardless of how you analyze, the result should be very similar. One drawback, the reason we are using FSL is that one drawback of AFNI is that it does not have a good package for ICA, right? FSL has a good package for ICA. SPM has a good package. I should say the package is called GIFT. So those of you who use MATLAB can use GIFT, like GIFT. Like Vince Calhoun has written, has developed GIFT, right? So those are um, some ways to do. Okay. All right. Any questions? So again, like we can like click and then see what happens for different region. And the most surprising part about this is that across different subject, the patterns are very similar, right? So if on a different subject I clicked, I would see something similar to this, right? And so this is like another way to look at the brain connectivity, right? Um, so should we cover some lecture, or have everyone, all of you, been able to generate the maps? Okay, so maybe let's try to do the second subject, right? Run the second subject, keep the original coordinates, and let's see whether we can replicate the results. Okay. So I'm just going to close AFNI.
So,
Yeah,
I have one question.
yeah.
Why we accept this time series from the mask image instead of the brain?
The what?
Like the question is say we need to change. We accept them series from the brain works using the mask.
Yeah,
But we know that the mask instead of the brain.
right,
So I'm asking the question is why do we need to accept the time series
right.
from the mask instead of the brain?
Yeah, no, the mask is inside the brain. The mask is inside the brain. And that mask is, you know, a radius of 6 millimeter. That is the mask. And once we have the mask, we take the average from each volume, and therefore we can get a time series corresponding to that mask, right? We then take the time series and correlate with every voxel in the brain. Yeah, where?
There's a question of the brain shape of the stuff. Brain time series, you see time series.
Here? Oh, okay. 1 second. Huh. Okay. Okay. Extract time series from all brain voxels using the mask. We need a masker that works on the whole brain using the mask we generated earlier, right? And func mask MNI path, data preprocessed, so brain masker, right? It is using these coordinates to generate the time series. Did I explain?
Can you explain more about this, the shape of the time series extracted?
Right. So in this case, we are using, there is a function called nifty masker, right? And what it does is that it will create the mask, like from the mask, it will generate the time series. Is that clear? Maybe someone else can explain. Maybe. So, so you're extracting from all brain voxel using the mask, right? So let me just, okay, so if this is the brain, right? So what it will do is it will create a mask, right, based on the coordinates and the radius that you give, right? And then based on this one, it will generate a time series for the entire data set. Okay? Yeah. Is that not clear? Maybe can someone, maybe Rahul, could you explain?
So maybe I was expecting maybe I have some image.
Okay.
And also from the image,
Which is the image?
from the image, I will enter this mask. Have the mask again.
Okay. This is the image,
Yes.
and the mask is.
So I have the image, then
Yeah,
I have the mask. So maybe I'll put that I need to know the image with the mask.
right.
I can match it so that I can extract this time series. But in that code, we just only load the mask. So my question was just confused. How from the mask we're going to extract this time series?
So, so first of all, you have an image and then a coordinate, right? Based on the coordinate, it you have a coordinate, and then the other parameter is the radius, right? A radius of 6. So it creates a mask, which is a spherical ball centered around that coordinate. Based on that, it will extract the mean intensity for each volume, and then from that, it will create the time series. Is that clear? Okay.
So this, like the kilometer,
Hmm?
once that figure, like 815.
Uh, so radius is 6, right? So here radius is 6. Just as an example, we can try a radius of let's say 8. Okay, so now it's a much bigger radius, right? Instead of 6, it's 8. And then what we can do is we can run the analysis and see what happens, right? Now the sphere is bigger, so the radius is bigger, so you have more averaging. But when you have more averaging, it is possible that you are taking voxels which is not in the sensory motor cortex, right? And let's see what happens. Okay, so this is, what was the threshold I had used? Uh, 0.3. And then if I redo this with 0.25, um, did we see a difference between between 8 millimeter and 6 millimeter? So, so you can do a comparison, right? So that's how when we when we use the term mask, it is the like at least the options that we give is to generate a spherical mask, right? Where we give radius as one parameter and the coordinate. Based at that coordinate, it will generate a radius, right? And it can be 6, it can be 4, it can be 8. You can try and see what happens.
So what I'm understanding is that the sphere is basically averaging out all the boxes within that.
Centered around that. Yeah,
So if I have a large sphere,
right,
I might go on including centimeter and finally objects also,
right,
which might bring out a different kind of weight.
right, right. So just to see what happens, what we can do is we had 8. Let's try to make it something crazy. 6. Okay,
So the whole sphere will become larger
like a like 36, right? S-
drop into the
Right. So now let's see what happens. Okay. So maybe not so good, right? This is 18. You can see a lot of things on the edge, which was not there also here. So what must have happened is that in addition to the sensory motor cortex, um, perhaps it has come to the edge, right? So when it comes to the edge, there is CSF and other, um, right? So which would make this image more noisier, right? So we can go back and try, let instead of, let's try 4, right? See, the questions you're asking are like quite good because like even in the field, like there is no consensus as to, whether you should be using a radius of 6 or 8 or 10, right? Because it depends on the region you want to study, and if the region is fairly large, it would be okay, right? But if the region is small, then you cannot do. And so in terms of, it's called region of interest analysis. So in that case, some have argued that we should take, like, find ways to not use a sphere, but take the whole region itself, right? Do you understand?
maybe the strip altogether
Yeah,
as one chunk and
right, right. So in this case, we are just taking one voxel, so it's going to be a little noisier, right? So again, so like these things has to be like we have to use trial using different ways to find out what is the one. So what some other um, groups have suggested is that, let's say this is the sensory motor cortex, just take the whole region, average the time series and do the analysis, right? And take the other side also, so you have left versus right, right? Can anyone think of a limitation of that method or a disadvantage of that method? Right. That is one. The other one is that it may be a circular argument, right? Because if I want to say that there is something unique about my left motor cortex, and I'm taking all the voxels from the left motor cortex, then of course the left motor cortex is going to have significant correlation because I have used all the voxels from the left motor cortex. Okay, all right. Okay. Okay. Any other questions? Ag- Please ask if you have any questions, because after this one, okay, I mean, we still have few other chances like tomorrow and Friday. No, tomorrow is Friday, right? Right. So there's one other day where you can ask, but after that, you would be like, you would have to decide how to process the data, right? Again, all the commands are here, but you just have to find out, like, you have to decide which steps to take, right? And for data, should you use, like, so that's where you have to decide what z value should you use, right? Should you use a spherical radius? If you use a spherical radius, should it be 6, should it be 8, or should it be 4, right? Those are the questions that you have to decide, right? So if you have questions, we can play around with that and then, see. Um, but anyway, I'm here. Right. Yeah, right. Um, so basically, the atlas that I had showed yesterday, um, the UO atlas, there are a couple of other atlases also. So in those atlases, different regions have been given a different value, right? So if I wanted to identify the left, it would be maybe 44. If I want to, right? So it will have all those values if I want to. So there is something called the gray matter atlas. It has about 400 regions of interest, 400 functional regions of interest. So based on what you are interested, we can identify those regions and get the average time series. So if you were able to do this one, perhaps you could run the second subject. Right. So it will take some time, right? Yeah. What is this place? Okay. All right. Okay. So you gave three options, right? So if all of you can get the second subject, whichever you want, I will buy you today. It's called Dihati Rasgulle. Okay, okay. All right. Yeah.
So I want to like,
Okay.
so if we are doing task, we are getting the same brain activation.
Right.
And now we are in the resting state data, we are getting the same thing activation.
Right.
So now, what is the advantage?
Right. Right. That's a very good question. So he's asking that with finger you can do movement and get activation, and with resting state you can also get activation. So why bother doing resting state? Why not just do activation? Anyone? Okay. So I would say that what he's saying, actually task has better signal to noise ratio. You can see the response going up and down when you tap your finger. So why would one do resting state? Anyone wants to help me out here?
Well, why would anyone even perform task from the resting
No, no,
state?
no, no. Let's keep the question you first asked. Why should anyone do resting state?
If you're doing the task without using, let's say you're saying that tap this, uh, tap your left hand, suppose.
Right.
In the functional data, there'll be other variable also input,
Right.
which is so the activations will be coming not just from the task of what they're supposed to do, but from the other factors as well. In the resting state, the functional activity which was happening, let's say the motor region, because of the finger tapping, that will be continued and sustained. So in the resting state, rather than getting the activity from all of the factors, including the motor response, you'll be getting only the motor response. So it's more, let's say, a pure.
Okay. Thank you. So that if you want to study sensory motor activation or sensory motor cortex, you want to identify, perhaps finger tapping is a good paradigm. But I would say that in many cases, right, um, for clinical population or infants, they may not be able to perform that. So that is one reason. The other reason is that from one resting state, you are not just getting the sensory motor activation, you can also get the visual cortex. You can also get the default mode, the executive network, and so on, right? So from one resting state scan, you can get like 20 functional networks. So that is like one way. So that is one reason. The other reason would be, let's say you want to study like complex motor activity among, uh, let's say, stroke subject and healthy control. In that case, you know, even if let's say I had a stroke and I want to participate in the study, even if I want to perform the task, I may not be able to, right? So it is not like I'm not able to perform the task, right? And the difference that I will get is not due to how good my sensory motor activity is, it's that I cannot even perform the task, right? So from those point of view, resting state may be a different approach. Uh, right. So when you are doing task, right, um, it would be, let's say, motor task. So it would only activate the motor, but at the same time, you don't know what you are doing to the other tasks, right? Again, motor is a simple example and it would be okay. But let's say I was showing you this disturbing pictures, um, like fearful pictures versus neutral pictures, right? So during fearful pictures, it, it is quite possible that other networks, like my emotional network and so on, would also get affected because I'm performing this visual task, right? Um, but for resting state, like everything is at baseline, so like other networks are not going to get affected because you are stimulating one, right? So everything is present and we can map everything at the same time. But for task, we would typically have to focus on one network at a time. And that's one. Second thing is you cannot always assume that the other networks will not be affected. Any other questions? Right, right. Say that again. Right, 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 right. I think you can, right? You can, but um, I okay maybe okay. So I think maybe what you're asking is a little different. It's like if the question you want to ask is during fearful versus neutral images, what happens to the salience network, then you can look at the task regions and generate one. That is true, right? But that is specific to the task, right? And it may not be the default, right, state. So as an example, let's say you were to show fearful images and neutral images to someone, let's say, with anxiety disorder or schizophrenia, right? And let's say you saw there was a difference, in the salience network. What can you tell? You can tell that, okay, when the stimulus, you presented the stimulus, this is what you get, but it doesn't tell you whether it was like that before, right? You cannot tell whether like the stimulus caused this, right? To answer that, you would perhaps first should do resting state and then show what is happening, right? And then when you show the stimulus, and if you showed that, the strength had increased or something else had happened, it would be useful. And so for many cases, I'm not saying you should not do task. You should do, but I think you should also do resting state because it gives you a baseline, like the intrinsic network, right? You know how the network is, um, like during baseline condition, and therefore, right, because between healthy control and, let's say, schizophrenia, there is a difference in the network connection. I would argue that the difference that you see during task is because of the fact that these networks are different during baseline condition, right? So it would be like you have built a transistor which is faulty, and now when the signal, you're getting signal, it makes a different kind of noise, right? And therefore, because of this faulty circuit, is what is giving rise to the change in like the tone of the. Did I confuse you? Okay. Anyone else? Okay. So I think maybe just make sure that you have gone through this and generated the connectivity pattern for the second data set, right? And if you have done, just send me an email with a screenshot. So can I ask you a question? Do you think it's more difficult to be a graduate student now, or was it is it more difficult now, or was it easier back in the days when I was a student?
Back in the day, the technology was not as great how that
Right.
for a correlation we have back now
Right.
the competition.
That I think that I agree that, before, like, I had, I think, as I said, it took me 2 years to publish, and I think no one could scoop me because, okay, maybe no one was interested, but even if someone wanted fMRI data, it was not easy to get access, right? There was maybe 5 other places, at least when I was doing PhD, where people, maybe 10 other places where students had access to fMRI data. Now anyone with an internet connection can, download and analyze the data. It, right, that never happened, right? And perhaps maybe my um, uh, what I would say is that maybe AI is not going to replace me, but someone who knows AI and is like me can easily replace me, right? So unless I get used to AI, then, someone, with half the skills can easily replace me. It's like, yeah, it's like I have seen how AI has become like 6 months ago to now, right? Such a such a dramatic change. Like, so how many packages AI LLMs to use? Like anyone, all of you have used ChatGPT, right? And have you used Claude, Gemini, Perplexity, right? Which one do you like the most? Hmm? Claude? Okay. Yeah. It's, the thing about maybe we should switch off. Uh, I think we are done. We are done.